And our next speaker is, opening network keynote overview of cyberspace infrastructure and breadth of its application, presented by Dr. Jeffrey Fox, Professor of Computer Science and Physics from Indiana University. Now you see how computer science and physics come together, work together. So here's the sample right here.
Okay, thank you very much. Difficult to follow that inspirational talk, so I will try. And I will talk about, from a somewhat broader context, about cyber infrastructure and its application. And I've been working on computing and science and things since mid-60s, so I at least have some experience. And I started off in physics, and I'm now in computing. All right, so if we look at the day, I say I went into computing in the mid-60s because I thought it was pretty exciting. I would say it's even more exciting now. The rate of change is greater, not less. I thought it was pretty good then. And I was one of the early innovators at my university and was telling people to use key punches, not paper tape, which is what we used to use. So I've always been at the forefront. And now, of course, we're switching from this type of big fat laptop to iPads and things like that. So, all right, so if we look at the trends, they are an incredibly important trend is data. The world is now full of data from in all sorts of contexts, not just science. The largest, actually, as we'll mention later on, the largest source of data is at least accessible, useful data is the internet itself. And the largest actual application, computing application in the world is processing internet data. There is an important technical development, which, from a computer science point of view, namely that every chip you buy today has lots of cores. This laptop has 8 cores on it, and you can buy servers with more cores than that, and that number of cores will increase. Another important area which I will spend some time on is clouds. And clouds are pretty important for many people here because there are a lot of jobs in clouds. There are many millions of jobs expected to be created in cloud computing because it is the dominant way of doing computing commercially, and it's essentially a model for how to build data centers. The other important area is the one I started with, namely lightweight clients, iPhones and iPads, and I have the equivalent Android version of both of those too. And another interesting feature of today is I used to work on parallel computing. At the time I did parallel computing, I would say that was led by universities and companies followed. Today I would say the opposite is true. The companies are actually leading a lot of the innovation, and universities are doing fine in applying those innovations to university-related areas. But the actual core technology is probably being, you will find the key papers, if you look at the key papers in how to do lightweight clients or how to do clouds, they're going to come from Apple and Google scientists. They're not coming from, there are some from researchers, but the critical papers come from industry. All right, so here's some comments on data. So it appears that, I mean, the trouble is these numbers are so big that you don't know. So I mean, this machine here has a 100 gigabyte disk, and we are creating 1,000 exabytes of data a year. That's the world, and that's quite a lot of data. And now I will have a slide a little later on giving one example of where this data increase is dramatic. And say the computing. But this is just a bunch of sort of snippets here. The largest science application is probably the Large Hadron Collider at CERN, where they're looking for the so-called Higgs boson. That only has 100 petabytes of data, which is less than an exabyte. So that's sort of negligible. And Google is already processing that type of data every day as when it's delivering your search results to you. And so here we have all sorts of examples: the web, video from unmanned aircraft, relevant to everybody and then really important is healthcare, where you have both medical records, but the largest source of data in healthcare is likely to be genomics, because your genome takes a lot of data. And soon everybody will be able to have their own genome, and processing that and understanding the implications of that will be an enormous project, and that will, in my opinion, use clouds. We know that Twitter is very important and the related technologies, and there's sort of interesting research pointing out that you analyze what's happening on Twitter, you can predict things like where there's going to be where the flu epidemics are, because the tweets are correlated with how people feel, and they'll discuss their illnesses. And so by actually analyzing things like tweets, people have shown you can predict which stocks will go up and down, and where you need to worry about the next diseases, and so on. And then we have these other many scientific applications. So this particular slide is a little technical, but it just comes back to this multi-core issue. Namely, it used to be that Intel made computers that got faster and faster by building cleverer computers. But unfortunately, they couldn't build cleverer computers. They ran out of new ideas, and so they actually built the same computer, but replicate it many times. That's why you have multi-core. And so we have basically an agreed computing unit. Well, we have actually multiple versions of it, of that. And we're bound to have multiple computers available to do things. And that's important because it says that we need people who will actually take existing applications and reprogram them, because using lots of computers at the same time, that's what's parallel computing. That's a pretty hard field in computer science. So here's an interesting graph from NIH about the importance of data. So the thing at the top, the straight line, is called Moore's law, and it basically tells you how the cost of computing is decreasing exponentially. This is, think of the left hand, the axis as the cost of something or other. So that's Moore's law, which says that the cost of computing halves every 18 months. Well, the diamonds are the cost of finding your genome. And you will see they've gained a factor of 1,000 over the last couple of years compared to computing. So this has two implications. One, that's the big data implication. Each of those genomes still takes the same size. We can do it 100 times cheaper, which is and it will get even cheaper, which is why we can do it for everybody and revolutionize healthcare. It also means there's a very important challenge in the field, in the research field, is how on earth can you possibly process all this data? Because that's a problem. Data is increasing faster than computing. Computing is at best getting Moore's law, which is not really a law, it's an empirical observation. But there ain't much we can do, except we can do a factor of 6 by using GPUs, not CPUs, but there's no revolution as far as I know expected in computing. Whereas we're having revolutions in data. All right. So what is cyberinfrastructure? This is a magic word from NSF. It is called e-infrastructure in Europe for the same concept, and it is by definition the infrastructure that supports distributed research, learning, and commerce. And that infrastructure has some components. We heard about the network component. There is also, of course, the computing component, and there's even equally important the software that goes on top of it. So the cyberinfrastructure refers to the base hardware, networking computers, and a layer of software typically called middleware, which enables you to use those resources to do nifty things. So that's cyberinfrastructure. And cyberinfrastructure, interpreted broadly, stems over a wide range. It stems from things called supercomputers, which we'll hear more about, And in my opinion, it also includes what Google and Amazon does. I would say Amazon is using CyberInfrastructure to sell you books, and that's an example of CyberInfrastructure. And Twitter is using CyberInfrastructure to process your tweets, because all of those things are applications sitting on distributed network computers delivering value added to the world. So that's what CyberInfrastructure is doing. As supported by NSF, CyberInfrastructure tends to have an academic focus. NSF will support fundamental computer science research on the broad part of CyberInfrastructure, but NSF doesn't directly support Amazon. It does support using the concepts that Amazon uses to do better physics and better biology and better fisheries and aquaculture and things like that. It has these various aspects to it. It's distributed. We heard about how you have your network distributed across Arkansas, and that links to other networks distributed across first the US and then the world. So CyberInfrastructure is distributed, but it then integrates those distributed components together. So there is one world which we all live in, and we all wish to collaborate and interact with each other. That we see every day. It also has so-called parallel computing, which are these machines with technically, they're actually not so dissimilar from distributed computing, except the machines are closer together, they talk to each other much faster, and they're able to do a different type of problem, which is especially important in doing simulations. So what purpose of CyberInfrastructure is what I call more or less anything. And that is the application. That's what the Chancellor told us he needed here on this campus. It's what we just heard about that Arkansas needs. You need applications. So that's more or less anything. And that originally was popularized through e-commerce and e-business, and then e-science came from the United Kingdom around 10 years ago. But you can, I should have put down e-fisheries here as one of your primary applications, but I did put down e-fine arts because the dean was pretty interested in that area. So the goal is to build more or less anything, and you have to decide at Pine Bluff what your more or less anything is. Not everybody is going to do everything. And a critical feature of this is what is very important to you about this. You will be able to link to the people doing the same thing across the world. I mean, what this does is enable collaboration, and that collaboration is enabled in several different ways. One is that the people can talk to each other, whether they're doing high-definition video conferencing, which I'm pretty certain Arkansas I think is supporting vigorously. But it also is supporting shared resources. So if you have, I don't know, medical record data in Arkansas, you can go. I mean, one of the few things that Indiana does better than most places is electronic medical records. So you'll be able to use CyberInfrastructure to compare your medical records with the world's medical records, and in particular Indiana medical records. And it allows shared resources. Actually, medicine is the hardest one to do for privacy reasons, but most other fields are somewhat easier than medicine. And a good example of that is, of course, the web. Google shares and Microsoft share the web sites with you. So this is the two key features of CyberInfrastructure: sharing people and sharing data. And I guess the third one is actually using shared resources. NSF and others have these resources, computers, which you can use to process your data. And indeed, clouds are the commercial approach to that, where Amazon, Microsoft, and Google and others have huge numbers of computers. I mean, Google has millions of computers, and Microsoft and Amazon are not far behind. And those computers are just sitting through your network connection, and they will either give away free or sell use of them. All right, so that's it. So here's some examples of effectively the broad-based definition of cyber infrastructure. We've mentioned video conferencing. Digital libraries are basically the distributed digital libraries, the shared information resource. I would view Flickr, YouTube, Amazon as examples of commercial cyber infrastructure. An example which Department of Energy is putting huge resources in is using cyber infrastructure to design the next generation of battery, because they want to do a complete simulation of a battery from ab initio to get the best possible battery, which will obviously be important in this world where we have a lot of problems with power. So that requires parallel computing. I will mention a little more about data from the world's telescopes. I've already mentioned analyzing your genome. The next bullet is the most important. It allows you to be equal partners. It used to be you had to all live in Harvard if you wished to be competitive in research, because the other people that were good at research were down the hall at Harvard. Right. But everybody is equal on the internet. Harvard actually doesn't have any advantage. So you have no problems. You just need to harness these resources. And you can collaborate with anybody and access any data, and it's a great equalizer. This is basically the fundamental premise behind this project we have, MSIC, that this type of technology is an equalizing technology. And I gave you already the example of a cyber infrastructure use of analyzing tweets. And you can also analyze documents in a similar way. Little projects which some of my friends are involved in is trying to understand which is the world's best university, and a lot of the input from that can just become from taking from data available on the internet, who's published what where, and who references what where, and how much money people have got. All that's on the internet. So you can just process the internet and come up with saying XYZ is either the #1 hospital or the #1 university, because that's all data-driven research which can be gotten by sophisticated analysis of data on the internet. So here's this astronomy example, and this comes from Fran Berman, who was at San Diego, and there are, of course, lots of telescopes around the world, and those telescopes traditionally have come from different wavelengths. You have people looking in the optical wavelength, radio, infrared, ... And you get something like this, which is these brilliant experimentalists, observational astronomers. They here are looking at a part of the sky in different wavelengths. It looks pretty different in different wavelengths. And so this is an example of how the internet enables what's called the virtual observatory. Namely, people might make data. They put that data on the internet, and that then data can be compared by other people solely using the internet. It can be done from here. This data is internet accessible, and then you get science by comparing the results of existing data with other existing data. So this is a pretty good example. I mean, astronomy is always a safe one to do because the data is not proprietary. People don't make drugs out of astronomy data, so it is not hidden. I mean, there are some fields where this is actually quite hard, including the drug field, because there are both the people working in those fields view their data rather seriously. But astronomy tends to put their data out for people to use. Another example I already mentioned is the Large Hadron Collider. This is enabled by cyber infrastructure because this was the field I used to work on when I was a physicist. And I saw that one of the reasons I gave up was, I gave up when the typical experiment had 30 people on it. Now the typical experiment has 1,000 people on it, and they're basically enabled by, as you may know, HTML and everything was invented by CERN, where this accelerator now is. Tim Berners-Lee was there and invented effectively the core internet technology. And so these are 1,000 people. These experiments are enabled by the internet. And it's actually also computed on the internet. This is the so-called European grid infrastructure, which was developed to process largely data from CERN. And there are all sorts of statistics here. This particular set of computers is at 300 sites, 52 countries. Around 15 million jobs a month, etc. So, and I say this has far fewer, this is much smaller than what Microsoft and Google has to analyze the internet. That's a much bigger set of data. Let me skip that one. So here's the personal genomics example. These are genome sequencers which is pouring out more and more data, terabytes of data a day, and that data basically gets run through some compute pipeline, stuck on the internet by NIH, and then you get analyzed it, and then you have to have some visualization. Here's an example of which might be relevant to the fishery case of metagenomics. Metagenomics is a field where you take, at least if it's applied to the environment, you take samples in the environment and ask what genes do I have in that sample? And here's an example which has 50 different types of families of genes, and you can just analyze the set of, you just sequence them in one of these sequencing devices, then you can plot them in a nice visualization device, and you can immediately see that you have lots of different genes, and then you can use that, they can use that for actually disease studies, toxicology studies, because you can then correlate which genes are present with what other aspects, whether the fish are happy or unhappy and things like that. So this area of metagenomics is pretty important. You're going to get a talk from Jamie Powell. Let me talk a little about the work I do with Linda Hayden, who's actually at the University ECSU, which is not dissimilar from Pine Bluff. It's about the same size in North Carolina. And we have worked with, she actually came to one of the MSI-SEEK meetings a few years ago, and we started these projects to basically help her in her research with the University of Kansas to basically analyze data from the North and South Pole. So Kansas was building these detectors which can be used to find the structure of glaciers, and because glaciers are melting and nobody knows quite why they're melting. And Linda Hayden, who works on remote sensing at ECSU, I worked with her to show how to use CyberInfrastructure, and she is actually leading the CyberInfrastructure activities. And Jamie Powell this afternoon will tell you about that. So that's a good example of how a small HBCU is able to actually take a leadership role in a very prestigious project. This project at Kansas is a so-called Science and Technology Center, which is actually NSF's most prestigious award. And Linda is able to greatly increase her role just by using CyberInfrastructure. So here's the typical data you get from this, which is actually this is radar looking down, and that green thing or red thing at the green and red things are either the top of the glacier or the bottom of the glacier. And the goal of these experiments is to understand the bottom of the glacier so people can build better models of the glacier and its motion to try to understand why the glacier is melting, because it is melting, and the previous models were not getting it right. So this is science enabled by a rich set of cyber infrastructure. The data is taken at in Greenland and Antarctica and Chile, and it is analyzed there. It comes back, it is analyzed at Elizabeth City State in Indiana, and the results are then presented through the Kansas collaborators to the world. Another nice thing, another important thing for you to look into is visualization. Cyber infrastructure enables visualization, and a lot of the minority serving institutions have actually got one of these so-called tiled displays where you take a lot of standard displays and you join them together so that you can get, as you see, very large displays. So you can get very detailed visualizations of anything. Here we're looking at Greenland and some of the data from Linda's experiment. And I just have a person there so you can see the size of this display. So here is Jerome Mitchell, my PhD student. He was an undergraduate at ECSU, a master's at Kansas, as now he was admitted to the PhD program at Indiana University last fall. And so he works with ADME. I think you're part of ADME. And so he is actually delivering this so-called cloud workshop to ADME this summer at Elizabeth City State through their summer undergraduate research program. So these cyber infrastructures now is very nicely related to undergraduate research. And so let me just tell you a few bits about clouds. So why are clouds important? They are the commercial way of doing data centers. Because it's not quite obvious you need to have your computers next to you, because you can use on your network and access computers anywhere. And so the concept behind clouds is it is cheaper to put computers where power is cheap, power is green, and also you put so many of them there that they're much cheaper to run. A system admin can run, if they're already running 20 clusters, they can probably run 100 clusters with no more effort. So the typical estimate is it's 5 times cheaper to run hardware placed in these centralized places. So that's why there's a huge interest commercially in clouds. And you know, the typical computer center here is 11 times the size of a football field. Wow. And here is an example of a Google warehouse of computers on the Columbia River in Oregon. And another amusing feature of these machines is they use interesting technologies. You do not buy computers by the computer or by the rack, you buy them by the shipping container. So that was a brilliant discovery that Sun and others made. You just have your data center set up so the truck wheels in a new shipping container of computers, you plug it in and you're ready to go. And this is all due to economy of scale. And this then, this is a rather technical slide, but all it's saying is that this is what is meant by as a service. That these computers are sitting there with a place you don't know where they are. They're running software which has already been pre-installed there, and that software is just accessed, if you do it through Amazon, by a credit card. Although Amazon just rejected my credit card, I don't know why. But that is fine. They keep sending me messages, I don't like my credit card. But I only have a charge of $1.82 because I didn't use it very much last month. But anyway, this is a pretty important idea that anybody can come along with whatever normal charging or identification mechanism you have and use these computers in the sky, and you can have their you can run your chemistry simulation there, your Google Docs effectively is Microsoft Word in the cloud and things like that. And also the people who still have iPhones or other things, like my Android phone is backed up to the cloud. It basically is a Motorola phone and it is run off the cloud. I don't have to back it up, it is backed up automatically by Motorola. And that's this model of sensors as a service, that the cloud sits there and provides all the back-end information, and these tiny devices of the new lightweight client world, which include either the radar from Crisis, our ice sheet problem thing, pouring data into the cloud, or your iPhone or what have you, or your tablet. So this is the model. And another device we could even mention would be these genome sequences. These genome sequences would just pour data into the cloud. All right. So for the students here, we note that clouds are jobs. Clouds are not some random academic quirk, according to these major industry analyses. Clouds are already some 10% of total IT investment. There is a study I found on the web which said that this is sponsored in Europe, that there will be 2.4 million new cloud jobs in Europe by 2015. And we've just started offering cloud computing at Indiana, and it's extremely popular with our master's students and undergraduates for trivial reasons. I mean, there are real jobs here, and people aren't being trained. I mean, so by training people in these areas, you can actually get them jobs. So I will just point out there's a Gartner analysis of the status of technologies, and they have these various things transformed by the benefit versus the time scale, and cloud computing and tablets are transformational 2 to 5 years. So that's the lightweight client and the back-end cloud are the trend of the time. And they're going to make huge impact on this time period. And they're presumably going to stay in some form thereafter. So anyway, my student Jerome Mitchell is going to teach students how to do cloud computing at ECSU. I do not know whether ECSU will video conference it, but this is an ADME workshop, and maybe it's too late. I don't know whether you have students involved with ECSU, but we can obviously offer it other places, and it's basically, as I say, it's to introduce ADME and ADME students to the concept of clouds. And he's one of my PhD students, so he's meant to know about what clouds are, because that's one of my research areas. And so let me just, so this is maybe more relevant to, some relevance. So we are trying to work with Linda to actually offer cloud computing to minority-serving institutions. 15 years ago, I offered the first course on Java at Jackson State University. I was at that time at Syracuse University, and I used the internet with 100 kilobits per second to offer Java, and actually several Java courses to Jackson State, and then the Jackson State faculty members sat in on those courses, and then they took the materials and re-offered it themselves in later years. So the idea was not that people like me would take over the instructions at MSIs, but rather we would kickstart them, because I have the advantage of federal funding, so I'm able to spend more time studying research areas and therefore learn about these new things a little quicker than the smaller universities. And so anyway, we're going to try to do something like that with clouds, where we develop cloud, we take our current cloud courses, work on them to make them suitable, and then deliver them first to ECSU and then later to other ADME institutions. And I think what's the time? Is that the end of my time? Yeah. No, I'll stop there. So thank you very much. I'd be happy to answer any questions.
Yeah, I'm going to go the last one before the break. Introduction to TeraGrid. Presenter is Dr. Jim Ferguson, Director of Education, Outreach, Training from National Institute and Computational Science, University of Tennessee.
Well, thanks very much. My name is Jim Ferguson. I'm here from the University of Tennessee and actually representing the TeraGrid today. So if you're looking for certain things, there are a lot of things you can do with your research network. The TeraGrid is, you can think of it as being just one thing of so many other things you can do with your research network. Now, Jeffrey gave a great overview on what is cyber infrastructure during his talk, so I'm not going to replow that ground. The TeraGrid embraces the cyber infrastructure, combining computers, data, instruments in the field, different types of networks. I must admit that I do prefer the European E-infrastructure to cyber infrastructure, but maybe that's because I'm old enough to remember when cyber meant robots. So let me talk about what the TeraGrid is. It is a collection of resources supported by the National Science Foundation. In this case, it's mostly networking and computing resources, high-end computing resources. So they are integrated in among different facilities, and they're out there for your access, for everyone to use. They are, in many cases, large systems, or they're large data collections, or they're specific, in one case, a specific unique type of instrument that are available to be scheduled and used, all connected via software, via middleware, and via high-performance networks. The last bit here, my talk about the TerraGrid. The TerraGrid is actually going to finish up here on June 30th. But don't worry, there's another follow-on project funded by the NSF that'll start immediately after, called the TerraGrid XD, and we'll hopefully push these along. So here's sort of just a rough map of all these different resource providers, they're called. They can provide computing resources or instruments or data resources around the country. Again, these are for free, okay? They're available to researchers across the United States. So the objectives are mainly to advance science, advance computational science. So as the slide said, deep science with a lot of impact. Now, these resources are unique. A lot of the computational resources, sort of in contrast to the cloud computing that Jeffrey was talking about. These resources are large systems with tight interconnects. So you do things on these systems that you can't do really with cloud computing. Now, there are, legacy over the years. There are many people who are doing large amounts of science on these NSF resources that are really just using a large number of, say, jobs on a small number of processors at a time. Those researchers and the way they do their research would actually ideally now be moved over to more of a cloud model. Whereas researchers who need to use a lot of processors at the same time need these sort of somewhat specialized computing resources. So let me, just a little detail on the computing resources. Sort of the two largest systems that are out there, most capable, are down at the Texas Advanced Computing Center and at my center at the National Institute for Computational Sciences. So both of these systems actually at their heart have AMD microprocessors. The difference in between them is the way that they are put into boards and the network interconnect. To be blunt about it, the Cray system that we have in Tennessee has a faster or a more connected interconnect, and therefore we have a much easier time to support larger jobs. That's it's not to say that the Ranger system at TAC is not doing a lot of work. It's doing a huge amount of work. Both these systems are, and their utilization rates are very high among the community. So there are some other resources that are out there. Actually, in the XD realm, these data analysis and visualization resources are available. They were separate awards also actually at TAC and NICS. Jeffrey had a quick slide that showed some experimental systems that have been put out there, and they'll eventually graduate into resources that will be available on the TerraGrid. And they're at San Diego and Indiana and at Tennessee. Also, other systems coming online funded by the NSF, newer systems at Pittsburgh and at NCSA at Illinois. So the hardware over the years in these different programs rolls over. It ages fast. This high-end hardware. So what can you do to get started? as I've mentioned a couple times, these are free for use by US-based researchers. The second bullet is probably the most important one. I might stop here. So startup accounts and education accounts. If you can think of getting on, if you think of getting on these large resources is very hard to do, maybe it's a high bar. That might be true for the third bullet here, for the large TeraGrid Resource Allocation Committee, when you're going to do your science on these large resources. But for the education and startup accounts, it's been purposely set very low. Okay, so startup accounts for you to try your applications on these systems really requires a couple of paragraphs of a description of what it is that you're working on. What's the science that you're doing? Describe how you've been using it. You've been using your resources, maybe a package that's a common package that's out there, maybe a code that you've written and you use all the time, and describe how you're outgrowing your department or your school's cluster, and I really need to try this out on larger resources. And you send that in, and those get approved very easily. I mean, every center has a committee that looks those over every week or every 2 weeks, and approval is quite easy. And the same for education accounts. We support classrooms around the country. I can tell you at NICS, because I've delivered some training, over the internet to Brown, to Truman State up in Missouri, to Morehouse down in Atlanta, to Wofford College, Wofford University, in South Carolina. The list goes on. That's just for our place. All these other centers also support college classrooms every semester. So, and it doesn't have to be, I can say for sure, almost for sure, that 98% of the students, they don't need to be on a huge supercomputer to do their homework, okay? But the fact is, what this is doing is giving them some experience, and to take the mystery out of, oh, that's a big system, it's probably going to be hard to use. Well, it's not any harder to use than your departmental or your desktop machine. At least that's what we try to make it that way. The 62 undergraduates up at Truman State in Missouri who are studying chemistry this semester, they all did regular bench work chemistry in the first semester, in the fall semester, and now they're doing the computational chemistry to mimic what they did in the fall and the spring. And their professor asked if they could get on and use Amber, which is a standard chemistry package, and that was not a problem. We delivered a little training to them, and she's actually, with a class that big, obviously she's not having them go off and do a lot of different things in Amber. She's trying to keep things focused. But the fact is that these systems are available and out there, and if your capability at your campus is not flexible enough or easy enough to use, this is another option out there for you. The third bullet there is if you graduate from your startup account, you're doing some research, and you're ready to try to get a lot of time or need some big resources available on the other systems, that's when you need to put in a proposal to the TeraGrid Allocations Committee. And they meet once a quarter, and all the centers, including our centers, if you are doing that for the first time, there's actually a whole guide on teragrid.org on how to write a proposal. But you can also call some people up, and they'll be happy to help you write that proposal and guide you. So Among the other things we do, we help new and established users. Let me point out the science gateways. The gateways are, well, you can think of as portals, or some people like to call them fancy websites, but they're really more than that. There's a lot of work behind the scenes at these gateways, and there's more than 30 of them. I'm pretty sure that are mature, that are out there in different areas of science, multiple in some sciences. They provide sort of a collaboration space for different people in certain areas, common areas. They can come in, they can put tools in, they could put in data sets, they can get community data sets and use that easily, all within these portals. And they all have different types of capabilities, so they're not cookie cutter type things. But what the objective of them was to make doing the particular science that you would like to do on these large resources much easier. So you didn't have to learn quite so much of the nuts and bolts behind the scenes. HPC University I'll mention in a minute. TerraGrid has some other web resources, and these will continue going forward in the next instantation of TerraGrid, as far as having a knowledge base and a user portal that's on the site to make it easier for people to come in and go to the different systems that are on the TerraGrid. So I mentioned Science Gateway before, and the different ways that they are used. There are quite a few out there. If you take a quick look, and you can find some more information on the ones that are most heavily used. If you look at TerraGrid, terragrid.org, and look under the Science Gateways. Well, let's mention, how can it help? I mentioned these before. If you use the same tools, if you have a very complex way that you need to move data in and out, these things can help. And they provide access to, in some cases, they have sort of pseudo community accounts to come in and be able to run on different resources on the TerraGrid. The TerraGrid has an annual conference each year. We have opportunities for students and for educators there, as well as researchers in the field. I would encourage you to take a look at to have a look at the TerraGrid 11 website. See if you might want to come and visit. See, it's in mid-July in Salt Lake City this year. I mentioned the transition from the first TerraGrid program to the second one. Obviously, that's going to be sort of a main theme at this TerraGrid conference. But there'll be also many opportunities for students. They're out there right now, actually, for doing posters and for workshops and for student volunteers. So I would have, if you're interested at all in the student program, I would encourage you to take a look very soon in the next couple of days here. There's a lot of supported supported student activities at TerraGrid each year. The Campus Champions program is a particular part of TerraGrid and the EOT program there. We try to recruit people on various campuses to represent the TerraGrid, to stay up with the latest news and the latest actions and technologies in the TerraGrid. So if you're on a campus, you can find your campus champion and get the latest news and other guidance for TerraGrid. So I don't know Keith or Albert, but I know they're listed as the UAPB campus champions here on the TerraGrid website. There's another one sitting right over here, too. That's Jeff Pummel.
There you go.
Not for this site, though, for a different one. Sorry, I was just flipping by. So, obviously, the various TerraGrid sites do education and training for these large computers. You know, they in many cases they have quirks that you know, require some more intermediate to advanced training to be able to use the systems in a most effective way, especially when you're trying to scale up code to tens of thousands of processors and get the most efficient performance you can out of them. HPC University is an online place. It's a nice resource for some online information and online tutorials. It also points to the CI Tutor set of online tutorials that that have been worked on by many of the TerraGrid partners and reside here and at Illinois. It also the people who maintain this site also maintain sort of up-to-date student, intern, and other type of opportunities here. So it's worth taking a look. The communities programs at the supercomputing conferences. That's the SC is, and this keeps flipping me. I wanted to just mention that in both the education and broader engagement programs that have been long running at the supercomputing conferences, different pathways into this community of high performance computing users. I invite you to take a look at these different opportunities. If you go to the SC11 website, which I listed here at the bottom, there is a communities tab there, and there are opportunities under both broader engagement and the education program for students and educators alike, and a lot of supported programs there. So please take a look at that and take advantage. This year's conference is in Seattle. All right, so I've whipped through that pretty fast. There are a few websites you might want to take a look at. I didn't even get a chance to talk about, say, the National Science Digital Library or CSERD, but those are some nice repositories for different educational training and other data associated with computational science. Thanks very much.